Hey there, Calc folks. Back here with another video where we're still looking at application of derivatives, but we are starting to wrap up that topic of functional analysis here. And in this video, what I would like to do with you is kind of go through the techniques that we've developed with functional analysis and the calculus, and kind of combine that again back with some of our algebra knowledge to do some precise graphing, right? And kind of look at these techniques in summary, right? With a few examples. I think I look at a polynomial example. I'm going to look at a rational example. And I also look at I believe, trigonometric function, right? We do look at a trigonometric example in this work. So it is really, you'll see here when I bring up my notes, just a few examples. There is not much to go back with and state again in terms of notes. All right. What we want to do is just consider applying some of the techniques we have along with techniques that we already developed back in algebra to begin analyzing our functions. All right. To begin with here, right, we might consider analyzing this polynomial function. Notice this is a polynomial function. This is a third degree polynomial. This is an x times an x squared term, which makes it a third degree polynomial. And we could expand it to see that third degree polynomial, but this factored form is a bit more convenient for us. If we remember from the factored form, it tells us where we're going to find our x-intercepts. Anywhere f of x equals 0 is where we will find our x-intercepts. And we can see that those x-intercepts will be from this first factor at x equal to -1, and at this for the second factor at x equal to 2. And a little more specifically, at this x-intercept of -1, we will actually cross through the x-axis, whereas at this x-intercept at +2, we will actually just touch the x-axis and bounce on the x-axis. A couple of other things we could potentially go back and note again was this was a third degree polynomial with some middle terms that really don't give us much useful information, but the end term, right, which would be 4 here, right? If we took 1 times -2 squared, if we took this constant of 1 times this constant of -2 squared, that would give us a constant of 4. And remember, in our analysis of polynomials, the factored form will give us our x-intercepts, but the unfactored form, the general form of a polynomial, will tell us about end behavior and our y-intercept. Here, the end behavior resembles the cube function, right? Meaning the left end will point down and the right end will point up. It'll look a lot like the cube function in that regard. And we will expect also a y-intercept at 4. So right there, we already have our end behavior, our y-intercept, and some knowledge of our x-intercepts in this function. All right? That is all information that we gain from algebra. Right? And that is the first bit here in my summary. From algebra, the following analysis can be formed. First thing we note is the intercepts are 0, 4, -1, 0, and 2, 0 over a domain from negative to positive infinity. The other thing we could have probably noted was our domain is everywhere from negative to positive infinity. It has end behavior described by the cube function, which means the left tail points down and the right tail points up, indicating a range from negative to positive infinity. We could also comment on that with our range. All that is information we get from just analyzing functions f of x here, right? The factored form, this factored form will give me my x-intercepts. This unfactored form will reveal to me the end behavior and my y-intercept. All right? If we then consider finding the derivatives, first and second, we can finish that analysis by finding our extreme values and our inflection points. And with our extreme values, we can determine whether or not we have maxes and mins and where those are going to occur. And with our inflection point, we can make comment on our intervals of concavity. Now, if we take the first derivative of this function up above, I could do that with expansion and finding the derivative and then refactoring, or I could, I believe, even find the derivative of this through just a little bit of product rule mixed with some chain rule here. And that will give me, for the first derivative of our function, 3x times x minus 2. And if I expand that and take its derivative, that will yield 6 times the quantity x minus 1 in its factored form. All right. What we do note is both of these functions, f prime and f double prime, exist everywhere, and that they only bring about critical points when x is 0 from this first factor and when x is 2 from the second. And we have an inflection point when x is equal to positive 1 from the second derivative seen here. If we start to put that together, right? If we take those two critical locations seen here in f prime at 0 and positive 2, and we substitute those into f double prime, we would see that if plugging in 0 here, I am going to get negative 6, which is going to be less than 0, indicating there I am concave down. And that means at x equal to 0, I must have a local maximum value. And when I sub 2 into the second derivative seen here, I will get positive 6. That's greater than 0, which means I am concave up on this interval. And at x equal to 2 on this interval, then, if I'm concave up, I must be at a local minimum value. And it can be concluded from the second derivative test that f of 0 is equal to 4 is a local maximum, and f at 2 equal to 0 is a local minimum value. Implying then that f is increasing on the interval from negative infinity to 0 and 2 to infinity, and thus decreasing on the interval of x given from 0 to 2. All right. In order to be a local maximum value at 0, you had to be increasing before 0 and decreasing after it. And in order to be a local minimum at 2, you had to be decreasing before 2 and increasing after it, which is what these intervals describe. Furthermore, what we can see is our inflection point in our intervals of concavity come from setting f double prime equal to 0, which is going to give us an inflection point at x equal to 1 from the second factor. In fact, 1, 2 is going to be our point of inflection in this graph. And if we note a little bit about the behavior on either side of 1, for values of x less than 1, f double prime is actually less than 0, indicating we are concave down in that region. And when x is greater than 1, f double prime of x is greater than 0, meaning we must be concave up on that region bigger than 1, right, from 1 to infinity. If we put all this together in the graph, we see these features illustrated in our graph. First of all, you can see our intercepts at negative 1, comma 0, 0, comma 4, and 2, comma 0 for our x and y intercepts. We see that end behavior does resemble our cube function. Right? We can see there the left end points down, the right end points up. We can see those extreme values we found at 0 and 2. The local max being at 0, being the value f at 0, which was 4, and the local min, right, being 0 when x is 2 in our function. Did I have that right above? Yes. F of 0 equal to 4 would be our local max, and f of 2 equal to 0 would be our local minimum value. We then see we increase from negative infinity to 0 and from 2 to infinity, and decrease from 0 to 2. And those features are seen here in this graph. We are increasing from negative infinity to 0 and from 2 to infinity, and we're decreasing between 0 and 2, right, along this x-axis. Here at x equal to 1, you can see I've illustrated the inflection point. This is where the graph changes from concave down to the left of that inflection to concave up to the right. And we can see that's where this second derivative test was able to tell us that this was a local maximum here because we were concave down on that region. And this was a local min because we were concave up. Right? We now have a rather precise graph of this polynomial function. Not only do we know the x and y intercepts, but we also know where those extreme locations are, specifically, and we know where our point of inflection is. And all of that is illustrated here in this graph. All right. That is the case for a polynomial example. All right, folks, let's look at another example here. This time, let's consider a rational function. I have here this rational function, 5x minus 3 divided by the quantity 2x plus 1 squared. Where we will notice this rational function has a, let's see here, is there anywhere it will equal 0? Yes, it will actually equal 0 when x equals negative 1/2 in value. We do have a domain concern come from this denominator. Anytime x equals negative 1/2, this denominator is going to turn into 0. And that will mean in our graph where x equals negative 1/2, we will have a vertical asymptote. We can also see that our y-intercept will be at negative 3 divided by 1 squared, or 1. So our y-intercept will be at negative 3. And our end behavior, because the degree of the denominator being squared is greater than the degree of the numerator being a linear function to the first power, our end behavior is going to have to follow along the x-axis. And then for an x-intercept, that's where our numerator equals 0. That's going to be at 3/5. 3/5 comma 0 is where we will find our x-intercept. All of that is just the analysis of the function that we have from algebra. All right. Again, from algebra, the intercepts are 0, negative 3. That's the y-intercept from this negative 3 in the numerator over this 1 squared in the denominator. And the 3/5 comma 0 from where the numerator equals 0 for our x-intercept. And this is all over a domain from negative infinity to negative 1/2 and from negative 1/2 to infinity, indicating a vertical asymptote is going to exist in our graph at x equals negative 1/2, and that is true. And then lastly, the end behavior will be described by the horizontal asymptote y equals 0, which is the x-axis. In our analysis. All of that comes from algebra. If we want to go further in the analysis, though, we need the first and second derivatives. Using a little bit of quotient rule, I can calculate the first derivative to be 17 minus 10x over 2x plus 1 quantity squared. And I can calculate my second derivative to be 8 times the quantity 5x minus 14 all over the quantity 2x plus 1 squared. I'm going to pause here and double check something. I'm going to double check those derivatives. All right, folks, as I expected, I did have my derivative wrong with this first derivative. This should be 2x plus 1 quantity cubed in the denominator, not quantity squared. I knew there was something off there. There is a factor of 2x plus 1 that cancels in the numerator there. And this second derivative is correct. We actually have two 2x plus 1's cancel in this numerator. We end up with these two factored forms. Again, what we will notice is both of these do not exist again at that vertical asymptote where x equals -1/2. And again, because we expect a vertical asymptote at that location. In terms of critical points, though, the first critical point will occur at 17/10. Right? That will be our critical point given by f prime of x equaling 0. Our inflection point, it's going to happen at 14/5. Our inflection point will be located at the coordinate where x equals 14/5. All right. If we start to put this together, right? So x equal to 17/10 and x equal to -1/2 are the only critical points, right? Where our first derivative equals 0 or does not exist. And it's already known that x equal to -1/2, we have a vertical asymptote. However, if we take x equal to 17/10 and we substitute it in here for f double prime, we will end up with the result given by -625 over 5,324. We do end up with a negative result, which is less than 0, which indicates in that region we are concave down, and at 17/10 we must be a local maximum value. At 1.7, at x equal to 1.7, f illustrates a local maximum. F at 17/10 gives us 25/88 if we substitute that into our function, and that is going to become the location of the local maximum value in our graph. We will be increasing, right, from -1/2 to 17/10, and we'll be decreasing everywhere else in our domain, from -infinity to -1/2, and from 17/10 to infinity. Those will become our intervals of decreasing behavior. The intervals being where we are bounded by these critical points of 17/10 and -1/2. All right, in our notation here. Now, if we do a little inflection point analysis, as we had noted, x equal to 14/5 is our inflection point where f double prime equals 0, and where x equals -1/2, we also have perhaps a point of inflection. If we do a little bit of analysis on each of those regions, we'll note we are concave down from -infinity to -1/2. And for 1/2 to 14/5, we are also concave down. And we are concave up for 14/5 out to positive infinity, because that is where we are going to expect f double prime to be greater than 0. All right. Again, if we do a bit of an analysis here, the denominator is always going to be positive. This first factor in the numerator will always be positive. What's going to determine the sign is 5x minus 14. When is 5x minus 14 greater than 0? Well, that's when x is greater than 14/5. We can solve that inequality and find that result. When is it less than 0? Well, that's when x is less than 14/5. We can set 5x minus 14 less than 0 and solve that inequality, and we will find x is less than 14/5. All right. But 14/5 down to our other, inflection, location of inflection given from where this denominator equals 0. At that vertical asymptote, you are going to have the potential for a change in inflection. All right? And I do believe we see that in the graph. If we bring our graph into the picture here, here's our graph. And what we do see to begin with is we do have that vertical asymptote at -1/2. We do have this y-intercept at -3 and this x-intercept up here. Where was that at again? That was at, wasn't it 3/5? Yes. It was where this numerator equaled 0 at 3/5. So we can see that's right about there is where our x-intercept would be if right here is 1. We had this absolute local maximum value right here at 17/10. That's 1.7. So right there before 2 is where we have that absolute max at 17/10. And you can notice we are decreasing from -infinity up to -1 or -1/2. And we are decreasing from that 17/10 out to positive infinity, which is what we said above. We're decreasing on these intervals, and we are increasing between -1/2 and 17/10. We are doing a little bit of increasing right in here between the vertical asymptote and this absolute maximum value. We are concave down from -infinity to -1/2. We see that in our graph. From -infinity to -1/2, we are concave down. And we note this is also true from -1/2 to this inflection point at 14/5. That's 2 4/5. That's almost 3. That's 2.8. That's right here in our graph. There's our point of inflection. We are concave down from -infinity up to that point. And then after that point, what we see is we are actually concave up. The graph gradually caves back upward after 14/5 in value. Right? All these key features in our graph could be determined by analyzing the first and the second derivative of our function. All right, folks, we got one more here. Let's take a look at this one. Like I said, this one actually, it's a little mixture here of both an exponential and a trig function. This is kind of a unique example. I say, let's just consider graphing f of x equals e to the x sine x over x in 2 periods of the sine function from -2 pi to 2 pi. All right. This is a revolution around the unit circle in the positive and negative direction. If we were to make a revolution around our unit circle in the positive or negative direction, one full revolution, how would e to the x sine x behave? Right? What would be the key features in that graph? Well, to begin with, we would be interested in our x and y intercepts. And what we'll notice is our y-intercept is going to be at 0, right? When we substitute 0 in for x, e to the 0 power is 1, but sine to the 0 power is 0. So 0 times 1 would result in 0. 0, 0 is going to be our y-intercept. And our x-intercepts, they're going to occur everywhere the sine of x equals 0. So that's at 0, pi, 2 pi, 3 pi, or in the negative direction, 0, -pi, -2 pi, -3 pi, and so forth. Where on the interval from -2 pi to 2 pi, that's going to be at all the multiples of pi. That's where we're going to find our x-intercepts. -2 pi, -pi, 0, pi, and 2 pi. Right? And that is some of the initial information we can gather from this, from algebra. That and our domain, well, the function exists everywhere from negative 2 pi to 2 pi. F of 0 is equal to 0. All right. And f of x equals 0 when sine of x equals 0, or when x equals pi times k, right? This multiple of pi. So in the interval from negative 2 pi to 2 pi, the intercepts are at 0, 0, plus or minus pi 0, and plus or minus 2 pi comma 0. Those are going to be our x and our y intercepts. Now, if we take the derivative of this function, first derivative is going to give us e to the x sine x times e to the x cosine x, which is e to the x times the quantity sine x plus cosine x. And if we go further and find the second derivative, that's going to give us 2e to the x cosine x. Where both of these functions exist everywhere in that interval from negative 2 pi to 2 pi. And they equal 0 in those intervals when these trig functions, the statement sine x plus cosine x equals 0, or this statement here where e to the cosine x is equal to 0 in the second derivative. Notice e to the x never equals 0. There's no way that it can ever equal 0, the exponential function. E to the x is always greater than 0. So the only way f prime can be 0 is if sine x plus cosine x is 0, which means the sine of x would have to be the opposite of the cosine of x. When does that occur? When is the sine and cosine opposite each other exactly? And that is when we're at multiples of, well, that would be at 3 pi over 4 and 7 pi over 4 in the positive direction, and negative pi over 4 and negative 5 pi over 4 in the negative direction. All right. I do note these do exist everywhere, and where the first derivative equals 0 is at 3 pi over 4 plus multiples of pi. So that gave us 3 pi over 4 and 7 pi over 4 in the positive direction, and negative pi over 4 and negative 5 pi over 4 in the negative direction. In this interval from negative 2 pi to 2 pi, those are our critical locations. All right, and we can actually use those to subdivide up our domain, or our interval from negative 2 pi to 2 pi, where we'll note f prime of x is greater than 0 when the sine of x plus cosine of x is greater than 0, implying that would be when sine of x is greater than negative cosine of x. And for x in the interval from negative 2 pi to 2 pi, that is in these intervals here from negative 2 pi to negative 5 pi over 4. The sine of x will always be bigger than the negative cosine of x. From negative pi over 4 to 3 pi over 4, the sine of x will always be bigger than the opposite of the cosine of x. And from 7 pi over 4 to 2 pi, this statement will always be true. As for intervals of decreasing, they will then happen in between these intervals, from negative 5 pi over 4 to negative pi, and from 3 pi over 4 to 7 pi over 4. They're going to occur where sine of x is less than the opposite of the cosine x. And that will occur in those intervals seen there. As for concavity, we're going to be interested in when does the cosine of x equal 0. And it's going to equal 0 at x equal to pi over 2 and multiples of pi away from that angle. So in the interval from negative 2 pi to 2 pi, that's going to be at negative 3 pi over 2 and plus or minus 3 pi over 2 and plus or minus 2. In fact, I could probably say that a little bit more condensed like this. So let's maybe just point that out. That's a little bit easier, more condensed way to say that, right? It's going to occur at x equal to plus or minus 3 pi over 2 and x equal to plus or minus pi over 2. So that does divide up our intervals, where we'll see the cosine of x will be greater than 0 in these 3 intervals, and it'll be less than 0 in these 3 intervals. Or, sorry, in these 2 intervals. Can I count tonight? So those 2 intervals being in between these others. All right. And we can see all this in our graph, all of these little key features. If you notice here, though, I do display these features into a couple of intervals. To display it from negative 2 pi to 2 pi, which we see down here in this bottom graph, the scale goes from extremely small on the left side of the x-axis or y-axis to extremely large on the right side of the x-axis, on the right side of the y-axis. So to avoid losing information in the scale, I did separate this into the behavior we would see in the graph to the left of the y-axis, where we would have very small scales for dependent values, and to the right of the x-axis, where we would have very large scales for dependent values. And over here on the small scale, we can see our, first of all, those critical points here and here. And on over here, that would be at here and here. And then we can see our x-intercepts here, here, and here, and here. And then we have our points of inflection here, here. Careful, here, here, and here will be our points of inflection. We're increasing in here and in here, which continues up through here. And we are decreasing from here to here and from here to here. And all that aligns with the intervals we saw above. And similarly, we are concave down, right, in the interval from here to here and from here to here. And we are concave up in the interval from here to here and here to here, and also out in here. What I also like to see in this graph is this is the first period, this is the second. And you'll notice in their scaling, when I scale to relatively the same size, they both resemble each other very similarly over those 2 periods. However, when examined on the same scale, they look nothing alike, because they are different in their scales to the left and the right of the y-axis. Again, that is all being caused by this factor of e to the x. Otherwise, sine of x would just continue with your sine wave. The e to the x is what that blows it up extremely large to the right of the x-axis very quickly. And e to the x is what makes it extremely small to the left of the y-axis very quickly. That e to the x as a factor is what's causing the left and the right half to not exhibit the exact same scale, but the sine of x is creating the exact same pattern, right, in either of those two periods. And that's some interesting behavior to note here. And collectively, we were able to put that analysis together in this case and the other two examples by analyzing, first of all the knowledge we bring over from algebra about x and y intercepts and end behavior and domain and range, right? And including now an analysis of f prime and f double prime. F prime being able to give us information about locations of extreme values, vertical asymptotes, critical points, I might say, and intervals of increasing and decreasing, which could lead to extreme values. And f double prime allowing us to test for extreme values and to help us find inflection points and our intervals of concavity. Each of these analyses put to use the original function f of x, its derivative f prime of x, and its second derivative f double prime of x. When analyzing a function f of x, you can analyze the function for its details from algebra, and then analyze its first and second derivative for these details that we've developed in calculus. And we see that done in each of these three examples here. All right. Folks, this brings us really to the end of functional analysis. What I do have to finish or to continue with is we are going to look at some optimization problems, where the optimization problems are going to make use of, again, some of those techniques we had for, well, I should say this, the first and second derivative tests. We're going to kind of follow through with some first and second derivative tests, looking at the case for optimization problems. So there's going to be a little bit more functional analysis mixed in there, but not so much to deal with graphing and coming up with a precise graph of a function, but more or less to analyze for extreme values. Because optimization happens at the extremes. Right? It's where we see an absolute maximum, right, value, or maybe where we see an absolute minimum value, or a local maximum or a local minimum value is where we're going to see extreme values or optimization. We might be trying to maximize volume to optimize space, right? Or maybe we're trying to minimize expenses, right, to optimize a budget. We're going to be looking at some optimization problems where those maximums and minimums are going to be found using some first and second derivative tests. And that's kind of where we're heading, folks. And then from there, we're going to get into, well, a few other topics, but not so much focused on the idea of functional analysis. All right. And I will develop all those as they come. So, folks, with that said, I will end the video here, and I will see you in the next one.